Good morning, class. Can you hear me?
Good morning, Doctor.
Okay. Yeah, can you see my slide?
Yes.
Yes, Doctor.
Okay. I have sent you this past year question, and if you refer to the attachments, okay, so we are going to discuss an example, okay, of this past year question, number 2. Okay, this is on a composite frame. Okay, we need to solve this structure by using the stiffness method. Okay, so let us have a look. Okay, and get ready with, your exercise book. We are going to do this together. Okay, so this is the problem. Okay, maybe we can try to let us read the problem first to understand what is our strategy, okay, for the solution. Okay, so if you can see that in this problem, some of the member element 1 and element 2, the member global stiffness matrix has been given to you. Okay, so in your previous class, you have establish or write the element stiffness matrix for frame structure. Okay, so you shall be able to know which template in your appendix to be used. Okay, if this is not given to you. Okay, but since K1 and K2 has provided in this problem, so means that we do not need to redo it again. Okay, so you need to always understand the question before you you prepare your solution. So if you can see that here, a composite frame carries a concentrated load of 15 kilonewton. Okay, so in this structure, there is only one load, which is 15 kilonewton. And this 15 kilonewton is acting at B only. So meaning that we do not have any intermediate loading. So Q naught in the frame structure in the analysis is not exist. So we do not need to calculate the vector of Q naught. Okay, so and then given the frame, okay, A is this value, I is equal to 6 times A. Okay, this is for frame. Okay, when you want to use this to calculate the member stiffness matrix, and also when you are trying to use this for your if the internal forces, okay, is required, okay, for this for frame, while for cable A is 3,800 mm squared, and E is constant. So if you see that A is given, I is given a value, but E is not given in a value. Therefore, E will be just putting in as a E, okay, in your equation, okay. So now this is the structure, okay. Let us read what is the question, okay. Okay, we are going to solve 3 questions here. Okay, using the stiffness method, establish the element global stiffness matrix for cable. Okay, if you can see that, this BD is cable. Okay, and AB, BC are frame elements. Okay, so element 1, element 2 has been given the matrix element stiffness matrix, okay, in global, but K3 is not given. So therefore, in this for this A, we are finding K3, okay, for this problem. Okay, so you need to do this very fast because only 3 marks here. Then write the reduced structure stiffness equation in matrix form and solve for non-zero degree of freedom. So non-zero degree of freedom, this DOF, okay, yeah, also known as the permitted displacement. Okay, nodes. Okay, so I will put here nodal displacement. So non-zero means unknown. This is unknown. I will put DUK. So we want to determine the DUK. So how? You need to write the stiffness equation. So it will be Q equal to K D plus Q naught. Okay, but in this Q naught for truss is subjected to if there is temperature change. Okay, if there is a fabrication error in truss. Okay, but Q naught for beam, okay, and frame is due to the intermediate loading. So in both cable and frames, these conditions or this intermediate loading is not found. Therefore, Q naught is equal to 0 in this case. So here we want to determine the vector of Q, the force or force vector or load vector, and the vector of D, okay, the displacement vector, and also the structure stiffness matrix. Okay, but if you can see that, write the reduce. Okay, reduce here means that the K is not complete. Okay, so if you can see that in this problem, the DOF, okay, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So the total DOF in this structure is 11. So meaning that this, if it is a complete structure stiffness matrix, the size of the matrix is 11 times 11. But you just need to write part of it and solve for the unknown displacement. So we will see how many unknown displacement, then the size will be that number. Okay, if there is a 3 unknown displacement, the size of the reduced stiffness matrix should be 3 times 3, for example. Okay, then we need to calculate the force in the cable BD. This is the internal force. Okay, FBD is the internal force. So this FBD is not the support reaction, it's not the displacement. Okay, this is the internal force, axial force. Okay. Okay, you can use the matrix in calculating the axial force that I have shown you in the truss analysis, or you can determine the support reaction at 10 and 11, then means that support reaction at D, dx and dy, then by solving the equilibrium of the joint D, okay, you can, means that method of joint, okay, you can solve for the member force, okay, at FDB. Okay, so yeah, if we have time, we can try both of this method. Okay, but let's see how. Okay, but I've tried this with other class. We managed to complete this solution within the time. Okay, but it needs helps from you. Okay, so that we can proceed. Okay, class, are you clear?
Yes, doctor.
Okay.
Yeah.
Yeah, let me explain on the element, the arrow, and how to number the DOF first. Because in this problem, the DOF is given to you. Okay, so we do not need, okay, to draw the DOF, the arrow for direction of the DOF, and also the numbering. Okay, it is all given. But what if it's not given to you? Okay, so the composite structure, there is not no difference, okay, in the procedure, okay, of the solution with other structure like truss or beam or frame. Okay, it is just a combination of this idea, the concept behind, and then we put it into this structure. Just make sure you understand, okay, the behavior of beam, frame, and also the cable. Okay, for example, we need to know that in beam, we can determine the shear force and bending moment. Okay, and the axial effect will be obvious if you have a lateral loading. If not, so we don't normally find the axial, okay, force. Okay, so for frame, we have the internal force like shear force, bending moment, and the axial force. Okay, for cable or for truss elements, we have only axial force. We don't have any shear force, and we don't have any bending moment. And one more thing that you have learned in the stiffness matrix is the DOF per node. Okay, so for beam, you have 2 DOF per nodes. Okay, so the direction is vertical and also rotation. Okay, if I put in the this direction, so this will be Y direction and this is Z direction. Okay, for truss, you has also 2 DOF per node. Okay, so which is at Y direction and at X direction. And for frame, you have also you have 3 DOF per nodes, which you cover the X direction, Y, and also Z direction. So you need to identify this element, I mean this structure first. For example, A, B, C are frame. So at their nodes, you put 3 DOF per nodes. That is why if you can see that there are 7, 8, 9, 4, 5, 6, 1, 2, 3 are placed, okay, at the nodes for the frame. Then you also identify that this DB is a cable. Cable is also a pin jointed element which is can be categorized under truss structure. So this, the nodes, we will deal with these 2 DOF per nodes. Okay, so meaning that at B, at least 2 DOF must be shown in this X and Y direction. So it has been shown here, 1 and number 2 at B. Okay, and at D, you put also 10 and 11. Okay, but if these are not given to you, you need to give a number. Okay, so we have a rules to give a numbering or coding, okay, to this DOF. Okay, remember we need to number the unknown displacement first, then the known displacement. So you need to identify which DOF is the known and which DOF is the unknown. Okay, so as my previous suggestion to you, okay, you can identify that from your support condition. So you can draw your support reactions, and that directions will be demonstrate or showing you that the direction at that location, the displacement are all known value, known as zero value. Okay, so let's have a look. For example, at A, we have AY, AX, and MA. These are the support reaction at A. Okay, so it also shows that the displacement at these directions are all not permitted. Okay, is equal to 0. So if I write it quickly here, 0. Okay, 0. Okay, theta A, 0. Similarly, you can find it for your CY. So these are the support reaction at C, and this direction of the displacement are 0. Okay. Similarly at support D, but now this is a pin support, so we have only dx and also dy. So this direction of the displacement is also 0. So once we know that this displacement have this non-value, okay, we name them later. So if you can see that this decay, the non-value, we have 4, 5, 6, 7, 8, 9, 10, and 11. And these are the unknown, the remaining, where they will be at B. There is no support constrain this displacement, meaning that at B, this point, okay, can move horizontally, vertically, and also in rotation. Okay, so this D1 and D2, D1 until D3, that's why it has been given the value. Then followed by the non-displacement. Okay, yeah, I hope you understand about this. And if you notice that there is no notes given here, okay, but there is no problem because the note, unless you want to explain on something, okay, what is the connectivity of the element 1, then it is needed. Okay, like for example, what is the element, the nodes for element 1, so you need to give a notes to it. Okay, but in this problem we may not need it. Okay, but I will just put it, okay, any. Okay, 1, 2, 3, okay, 4 here, in case we need to use it for our explanation. Okay, and then we have this element 1, 2, 3 in the square box, and then we have an arrow to indicate the I and J. Okay, be careful, okay, of this arrow. Okay, so then we can start our solution. Okay, let us start with this A. How to determine the K3. Okay, so please go to the appendix that I have shown to you. I have provided earlier. Okay, this page, appendix. Okay, so for K3 class, may I know which type of structure I shall refer? Dear template. Truss, beam, or frame? For cable.
Truss.
Okay, thank you very much. Yeah, as we said that cable has only exoforce, so it fall under this category of truss structure. Okay, like for example, strut element. Okay, so it's also fall under this truss structure, or tie. Sometimes if you see that tie, struts, okay, cable, okay, they are all fall under this. So now there are 3 templates to be, shown are shown here. Okay, K prime, T, and K. Do you know which one to be used to find the element global stiffness matrix?
K.
Yes, you are right. So K prime is referring to local. Okay, so K is referring to global. Okay, so when we want to form the this structure stiffness equations, okay, so for question B, we are talking about global, okay, global equations. Okay, so let us please take down this template, or referring to this template. If you see this template, we are going to put in the A, E, L, CX, CY, CX squared, and CY squared. Okay, so we are going to determine the CX and CY first. Okay, so okay, this is what we have done yesterday. Let me okay, Let us do this together. Okay. I need the value of A, E, L. Okay. Oops. Okay. So can you give me what is the A value? I will write it here. The area for the cable.
3,800.
Okay, 3,800. But it's in mm squared, right? Can we convert directly to meter square?
Times 10 power of negative 6.
Okay, how about E? E will be E, right? It is constant. How about the L? Okay, so this is not given the horizontal length of the dB, but you have a 45 degree here. So, okay, so we can know this horizontal dB is how much? Can you calculate? This is 45. Class?
7.21.
May you calculate again? 7
7.6.
point. Now I want this value first, not the length. This horizontal value.
4.
4 meter, yes. Okay, so whenever they have this 45 degree, the horizontal and the vertical length will be the same. So the length for the dB will be
5.66.
how much? Again, I can't hear you.
5.657.
Okay, 5.666, is it?
Yes, 2.66.
Yeah, 66 or 67 is okay, I think, for me. Okay, so now AEL is given, is determined. So now we need to determine the CX. Okay, so you can use the cos theta, okay, or you can use the coordination. Okay, so I will use the coordination here. Okay, so now I will put a reference at D. Okay, let's say I put it at 0, 0 at D. Okay, so when come to B, my coordinate will be, can anyone help?
4, -4.
Yes, you're right. So it will be 4, -4. So my CX calculation is x at the far end minus x at the near end divided by the length. Okay, so x at the far end, if you see this, this will be the near end. This will be the far end, right? Because the arrow. Okay, so what is the x at far end? It will be 0, right? 0 minus 4 divided by the 5.66. Okay, may you calculate this value? Okay, then I'll continue with CY, which is Y at the J minus Y at the I divided by the length. Okay, so Y at the J will be 0, and then minus -4 divided by 5.66. Okay, can I have an answer for CX?
Negative 0.707.
7, and supposedly this will be positive.
Positive.
Okay, so next we need to calculate cx squared, cy squared, and cx cy. Okay, so what is the value of cx squared, cy squared, and cx cy?
0.5,
0.5,
0.5, negative 0.5.
negative 0.5. All right. So now you have all this value, okay, from this template. You can directly apply this template. Now your elements you're finding for K3. So yeah, maybe I give you 2 minutes, okay, to complete this.
Done, doctor.
Sorry, yeah, I have I have off my mic. Do you get this value? A over L has been included in the this template, and remaining the E outside this bracket. Because K1 and K2, the E also outside the bracket, we want to make it the same. Okay, do you get this value?
Yes.
All right. How about others? Can I see if you have done, please raise your hand.
Done, doctor.
Okay. Yeah, if you have done, please raise your hand so that I can see who else is still progressing. Okay. Okay. We have a few more. We have half of the class, is it? Not yet done. Maybe All right. Okay. Maybe we give them a bit time while the maybe another 2 minutes. Maybe the one that have advanced. Okay. Please study on the vector of D and vector of Q. Okay. We're going to show that later. Okay. Okay, class. I suppose everyone has done this. So let us, do you get the same answer?
Yes.
Doctor.
Okay.
Yes.
So yeah, these 3 marks. So we are going to move to the problem B. Write the reduced structure stiffness equation in matrix form and solve for the non-zero degree of freedom. Okay. So let us keep this. So okay. Okay. So I think I have explained this before to you. okay, before we write down everything, this must be very clear in our mind. Okay, so in the vector, in the stiffness equation, we have Q equal to KD for this problem. So Q is the vector of Q, the support reaction or nodal loading, okay, which can be partitioned by the non-value QK and unknown value QUK. Okay, so you can make a partition here. Okay, then you can immediately know that the QUK is actually opposite with the DUK. Okay, so it must be clearly, okay, partition. Okay, if you arrange properly your DOF numbering earlier. Okay, and the QK will be opposite with the DK. Okay, in this system, later we will discuss how many D. Okay, here if you have DUK, the unknowns 1, 2, 3. Okay, so we are going to have another partition, the vertical line. Okay, after 3. So because the K matrix, if you can see that, it must be a square matrix. Okay, so if we reduce the matrix, okay, it will be also square. Okay, why we want to reduce the matrix? Okay, because in our problem, we do not need to find the support reaction. We just need to find the unknown displacement, which is this D1, D2, D3. Okay, therefore, the reduced matrix here will be 3 times 3 matrix only at this region, K11. Okay, so simple to say, if you have 5 D unknown, D1 to D5 is unknown displacement, so you just need to determine 5 times 5 your structure stiffness matrix. You don't need to calculate for the, for this case is 11, total 11 DOF. So you don't need to calculate for 11 times 11. Okay, so this will be quite time consuming. Okay, so now, but be careful, okay? Even though this DUK we want to solve, if there is some value at DK, for example, let's say at row number 9, okay, DK has value like, for example, support settlement, support uplift, let's say 2 mm. Okay, when this row 9 has value, you need to also take this column number 9, okay, at the region K12, okay. You need to also determine it because this value later will be multiplied with this row number 9. Okay, be careful. If this DK is 0, O0, so K2, K12 region, you don't need to determine. Okay, you just need to determine K11 region. Okay, so let us find this K11 region. Okay, so maybe we will. So let's do this again one more time. Okay, so I will call a friend from you to give helps here. Just anyone, maybe. Let me see. Okay, Farhana, are you here? Nurul, Farhana?
Yes, madam.
Okay, come. So do you know how to give a numbering to this member stiffness matrix? Give a coordinate? Yes. Oh, okay, very good. Okay, yeah, can you try for element number 1? Can you explain the idea for your class first? How shall we give a name to this K1, matrix? Will be from NX.
NX, NY, and then NZ.
Okay, what is NX, NY, and NZ? Near N?
Yes.
Yeah, this is near N. Okay, X direction.
Yes, and at X direction. and y is near n at y direction, and nz is near n at z direction.
Okay. How about the continuous?
Fx, Fy, and
Fx.
Fz.
Okay, what is Fx, Fy, and Fz?
Far n at x direction, and far n at y direction, far n at z direction.
Okay, so this is for frame. Okay, because at frame we have these three DOF per knot. So therefore we have X, Y, Z, X, Y, Z like this. Okay, so how about for this cable?
Cable only has x and y only.
Okay, so it will be NX.
And x and y.
Yes.
Fx and Fy.
Yes, thank you very much. How about for beam?
For beam, we have ny and nz.
Yes, yes, you're right. Thank you very much. Okay, so now can you give a naming? But I see you have a very good understanding. Maybe we call other to help. Okay, so thank you very much, Fana. So how about Azhani? Azhani, are you here?
Yes, doctor.
Yeah. Can you help to give the K1 numbering? Do you know how to do that?
Yes.
Okay, so let's give me how to fill in this K1 numbering. Where is the near end for element 1?
At A.
Okay, correct. So I'll put I here. So how about the far end?
Far n at B.
Okay. So can you give a name for NX is? So a tips for you is you look at the near end and go for the X direction and then Y direction and then the Z direction. The numbering is following, is within 7 to 9 here.
And X at 7.
Yeah, correct. 7.
And then and Y at 8.
Yes, correct.
And Z at 9.
Yeah, then how about the far end?
Far n, Fx at 1.
Yes.
Fy at 2 and Fz at 3.
Yes, thank you very much. Okay, so you need to write this as well. Okay, thank you very much. I will call the other to help. Okay, so how about Nurul Husna? Are you here? Nurul Husna, are you here?
Yes, madam.
Yeah, can you help us with this K2 numbering?
4, 5, 6, 1,
Oh,
2, 3.
wait. You're just too fast. Wait a minute. So where is the near end for element number 2?
4, 5, 6.
It will be at C, right? And the far end is
C.
at B.
At B.
Okay. Yeah. You start with 4, 5, 6, and
6, 1, 2, 3.
oh, thank you very much. Okay, so this will be 4, 5, 6, 1, 2, 3. So we will call another one to help for the truss. Okay, how about Nurul Aisha? Are you here? Nurul
Yes, doctor.
Yes, can you help me on for this K3? Where is the I value?
At B.
Wait. At B is I for element 3, and then J is at D. Okay, so how these namings can be done?
1, 2,
1, 2, correct?
10, 11.
10, 11. Okay, 1, 2, 10, 11. Okay, so now, we need to combine this into the structure stiffness matrix. Okay, but we don't intend to find for the full complete matrix of 11 times 11. We just want to find 3 times 3 matrix. Okay, maybe we can do it together. I will call another to help us here. Oops, I think redo this. Okay. Let me redo this. Okay. Okay. So maybe I will call now Aini Nadira. Are you here?
Yes, doctor.
Okay. Come. Can you help me to find this structure stiffness matrix? If you know that the structure stiffness matrix, we need to sum up all the member stiffness matrix. And everything here, we are talking about global. Okay, so can you help me on this K11 element?
K11 will be 2.95 plus
Plus
K22 2.95 also, and then K3 wait.
wait. K11, you need to 2.95 plus what?
2.95 plus 1.667 power of negative 5.
And plus
Plus 1.667 times 10 power of negative 5 and plus 3.36 10 power of negative 4.
okay, what you have,
Wait a minute. So 2.95.
Okay, 2.95. Okay, so I change my color. Okay. Yeah, please prepare for the second one. K12, this one.
2.95 plus 8.333 and then plus 3.36.10 power of negative 3.
I think we are at K12.
Okay,
2.95 plus.
Okay, one. Wait, madam.
Yeah.
2. So 2.95 plus 1, 2. So plus 0.
Yeah.
0.
Betul kan?
And betul.
Yeah.
So 1, 2 tak ada. And then plus negative 3.36 then power of negative 10.
Yeah. Can you give me the value?
So 2.94.
0.94, is it?
2.94.
2.94. Okay, so we know that this is mirror, so this will be 2.94 as well. Okay, so can you do for K13 as well?
K0. 0 plus 0.
K13 is this one. What I mean is here. Okay, row number 1 and column number 3.
Column number 2. Okay. 0.0176
Okay.
plus 3. 0. Row number 1.
Row number
0.05.
yes.
And yeah, no more.
No more. Yes, correct.
So
What is
0.0676.
0.0676. Okay, so similarly, it will be applying to here. Okay, so we will call another helper. Thank you very much. Okay, thank you, Aini. So let's have, how about Amalina? Are you here? Amalina, are you here? Okay, maybe we call Damia. Are you here, Damia?
Yes, doctor.
Okay, so maybe the remaining here, please help us. How about K22 now? I'm talking about here, K22. Row number 2, column number 2. Damia, do you know how to do that?
Sorry, Doctor, turn off mine.
Okay.
Okay, the answer is 11.28.
Okay. So please check. The rest are 11.28, is it?
Yes.
Okay. How about K23?
Negative 0.0176.
Negative 0.7.
0176.
0176. Negative 0.0176. Okay, so this is 23. 23 is this one.
433, 341.43.
341.43.
0.43.
Okay, so thank you very much, Damia. So right now we have solved for this structure stiffness matrix. If the problem requires for full, so we need to complete with the 11 times 11, okay, matrix. Okay, here. Okay, maybe we can continue with this displacement vector and the nodal force vector before we have a break of 5 minutes. Okay, so let me keep this. Okay, so I think we have very clear on which one is the unknown displacement and which one is the known displacement. Okay, so as we have discussed earlier, okay, B number D1 to D3 is unknown, okay, displacement, okay, and the D4, 5, 6, 7, 8, 9, and 10 and 11, they are all known displacement, known as 0, okay, the magnitude of the displacement is 0, okay, no displacement. So this is your displacement vector, D, okay, you can write it. But because of the reduced version, actually you just need to know the vector up to 3 only, row 3 only, okay, because we are going to use up to there, okay, but this is a complete of the displacement vector for this problem. Okay, so for the nodal force vector Q, okay, you also know that 4, 5, 6, 7, 8, 9, 10, and 11 are all support reactions. So Q4 until Q11, they are all unknown. Okay, and then 1 to 3, there are no support reaction. They're supposed to have 0, but there is one nodal force here, 15 kilonewton. Okay, and it is actually associated with this direction X, okay, at coding number 1. Okay, so therefore Q1 will be 15. Why positive? Because it has the same, the positive sign, okay, it's positive direction, okay, of these loads. So this will be the complete set of the nodal force vector, but later in the reduced version, we are going to use up to 3 rows only. Are you clear, class?
Yes.
Okay, so we will have a break of 5 minutes, then we will continue with the solution. Okay?
Okay, doctor.
Okay, Akila, are you here? Nurin Akila. Is here. Nurin Akila, are you here? Okay. Maybe I will just put it here. Mm. Mm. Okay. So this. Can we continue, class?
Yes.
Okay. So right now you can put your this stiffness equation in yeah, arrange your Q vector, arrange your D vector, arrange your structure stiffness matrix. In this case, we don't have Q naught here. This will be the form, I mean the matrix form. Okay, you expected. Okay, then you can solve for your D1 until D3. Okay, by using, I think directly by your calculator should be no problem. Okay, so do you know how to use your calculator?
Yes.
Okay.
Yes,
Yes.
Yes.
doctor.
For those who don't know how to use the calculator, please let me know. Okay, you can put in the WhatsApp room, chat room, no problem. So we will ask, yeah, your friends to help here. Huh? Wait. Okay, I will give you a 2 minutes time to solve the D1 to D3. I will show you the answer later.
Doctor,
Yes.
if let's say dia as full matrix, so
Yes.
that means kita kena buat sampai 11 lah macam tu.
Yes, betul.
Okay.
But the process is not difficult. The process is very boring and long, and your I think your main constraint is the time. if you are under test lah, of course. If you are not, if you have an Excel file, this will be done in a second. When you key in the input, everything will be out. So my assignment later, I will request you to do an Excel. I will tell you later about this.
Okay.
Doctor, how to
Yes.
change D3 into radian?
No. You just get the answer, and then the unit will be in radian. Because D3 is deal with the rotation. You don't need to change it.
Oh, okay. Thank you.
I mean,
Doctor.
in your calculator, the answer that you have obtained for D3, you don't need to change anything, but the unit is in radian.
Doctor,
Yeah.
I got for the 1-1, I
Yeah.
got positive 2.95. But
This one is wrongly. This is from my other class. Can we check again? Okay, wait. What is our calculation just now? Positive. 2.95. Okay, 2.95 positive. Then positive. The remaining is okay, is it? Only this is
Yes.
in this?
yeah,
Okay. So can you recalculate the things?
mm,
D1 6.89,
0.89,
D2 negative 1.8,
1.8,
D3 negative 1.5 exponent negative 3.
negative 1.5
Times 10 power of negative 3.
Okay, thank you very much. So once we have solved for the D1 up to D3, we can use this value to solve for our support reactions. I would like to show back this, the sketch here. Okay, so if you see this, the support reactions fall under 4 to 11. Okay, means that Q4 until Q11. So if you look at this arrangement, okay, D1, D2, D3 right now has been solved. Okay, and if you want to solve for the Q unknown, you need the region of K21, this one. Okay, meaning that K21 multiply the known value of the displacement, you will get your support reaction. Okay, so but now we don't need to calculate for all. Okay, because one of our strategy is to determine the support reaction at D. Once the support reaction at D have been solved, okay, then we can use the equilibrium at D to find our cable force. Okay, so now we only need to find Q10 and Q11 because support D we have only 10 and 11 here. So now for this we need to determine this extra elements in this K21 region. Okay, maybe we can do this now. Okay, so we continue with the 10 and 11. Okay. Okay, so maybe I will give you 2 minutes to fill up this 10 up to 11. Okay, and we will check it later. Okay, have you done that?
Yes.
Okay, yeah, so let us see whether you have the same answer with the previous class. Do you get this?
Yes.
Yes.
Okay, but the D, we have a new value here, so you need to copy this D1, D2, D3 to put in this. Okay, we are going to do that. Okay. Yes. Okay, do you know how to calculate this Q10?
No.
Okay, so this matrix multiplication is maybe I will write the equations down. Okay. It will be this one, the value this one, okay, multiply with this value D1. Why the whole thing? And this value number 2, okay, this will be with E. Okay. Multiplied with the second column, multiply second row. Third column, multiply third row for the equation number 1. Okay. Multiplied, then plus 0. Okay. You get the value. How much? Okay, I will be waiting you later. I will write the equations for Q11 for you to check as well. Okay. So basically they are all the same except the sign. This sign is negative, positive, and this sign is negative. This is equal to, okay, please check.
Negative 2.91. Negative 2.92.
Have any power or not?
Yes, power of negative 3.
Okay.
Next one is positive 2.92. Power of negative 3. Yes.
Okay. So what you have done here is to find the support reactions, okay, for Q10 and Q11. Okay, this Q10 and Q11 is actually your dx and dy. Okay, maybe to make sure you understand that, you can write it here. Sorry, I forgot. Dx. Okay, Q10 is actually your dx. Q11 is actually your dy, your support reaction. Okay. Okay. So then you can, use a method of join for join D to put in all the forces in. Okay. So I'm going to copy this. Let us draw the joint equilibrium. Okay. Okay. You can see that you are going to draw a joint D body diagram. Okay, meaning that this is D, and here we have dx. Dx is negative, means this direction. Okay, 2.92 power negative 3. Okay, and then 11 to be positive, that it's going up. 2.92 power negative 3. Okay, and then this will be F dB. Okay, we make it as assumption as a tension first. Okay, if you get the negative value later, means that you are having, a compression. Okay, so this is 45 degree. Okay, so now this is X direction, this is Y direction. Sorry, it's not Y prime. So you can make make use of summation fx equal to 0 or summation fy equal to 0. Okay, for this case, let us use the summation fx equal to 0. Then you can write the equilibrium, okay, for this. Okay, so FDB, okay, will be how much?
Times 10 power of negative 3.
4.43 times
4.13.
13, negative 3. So positive, is it? Is
Negative.
this negative?
Wait,
Positive.
Yes, positive.
Okay, positive means that this is tension. Okay, just put it tension like that. If it is negative, just put it in C. Okay, symbol of C means that it is compression. Okay. So I think yeah, that's all for the question A to C. Okay. Of course, you can use the matrix form to also find the FDB, but I found that probably this yeah, is also quite fast. Okay, yeah, you can, because D1 to D3 you already found. Okay, you no need to create anything new here. Okay, just to find maybe the more challenging is to find the Q10 to Q11. Okay, but if you have no problem with solving this multiplication, I think yeah, that's all for this. Okay, so you have any question for me?
No, doctor.
Okay, yes, I'm going to stop the recording first.